My name is Jacob Durant, and today I'll be discussing several computational methods for prioritizing potential inhibitors in preparation for subsequent experimental testing. By way of background, I'm a postdoctoral scholar in Dr. Romy E. Amaro's lab at the University of California, San Diego. Among other things, I'm interested in computer-aided drug design applied to infectious disease, especially tropical neglected diseases like malaria, African sleeping sickness, leishmaniasis, and Chagas disease. This presentation is divided into 3 parts. First, I'll describe an enzyme from Trypanosoma brucei called RNA editing ligase 1, or REL1, that may one day serve as the drug target of future antiparasitic medications. Second, I'll demonstrate how computational techniques that analyze known REL1 inhibitors can be used to identify novel inhibitors with improved efficacy or pharmacological properties. Finally, I'll describe how knowledge of a drug target structure can also help guide the computational identification of novel inhibitors. First then, let me introduce the REL1 enzyme. REL1 is critical for the survival of the unicellular parasite Trypanosoma brucei. As T. brucei causes African sleeping sickness, REL1 inhibitors have great potential in the fight against a devastating disease. Several previous studies, conducted by myself and others, have identified REL1 inhibitors that are effective in the low micromolar range. One of these compounds was even effective against the whole cell parasite, suggesting it was able to successfully cross the parasitic cell membrane in order to reach the intracellular REL1 target. Interestingly, all of these known inhibitors have a central naphthalene core, a flat substructure that may mimic the adenine ring of the endogenous ATP substrate. Given these known inhibitors, let me demonstrate several small molecule approaches that could be used to identify novel REL1 inhibitors. These approaches computationally identify novel inhibitors by considering the chemical and structural properties of existing molecules with known activity or inactivity without requiring any specific information about the drug target itself. Substructure searching is arguably the simplest small molecule-based drug discovery technique. For example, given the structures of known REL1 inhibitors, naphthalene-based compounds seem to be particularly effective. While not all naphthalene derivatives inhibit REL1, it's reasonable to assume that these aromatic compounds have a better chance of inhibiting the enzyme than compounds chosen at random. To identify REL1 inhibitors that can be easily synthesized using D3 reactions, one could search a large database of easily synthesizable D3 compounds for molecules with naphthalene substructures. Fortunately, just such a database is available online at the Collaborative Drug Discovery, or CDD, website. To search for naphthalene-based D3 compounds, just enter naphthalene, without explicit hydrogen atoms, into the online molecular viewer and click the Search Molecules button. In total, 3,032 D3 compounds match the search criteria. Prioritizing subsequent experimental work by focusing on these naphthalene compounds will likely yield a higher hit rate than would have been obtained otherwise. A second ligand-based approach involves searching by chemical property. The table shows the computationally predicted chemical properties of a number of known REL1 inhibitors. Again, molecules with similar chemical properties are more likely to inhibit REL1 than molecules chosen at random. To demonstrate, I'll perform a chemical properties search in CDD to find compounds with similar molecular weights, hydrogen bond donor counts, and octanol water partition coefficients. CDD again provides useful tools for this kind of ligand-based searching. I'll first limit my search to naphthalene compounds, as before. Next, I'll further narrow the search by selecting only compounds with chemical properties similar to the known REL1 inhibitors. Specifically, I'll choose compounds with molecular weights greater than 450 Daltons, log p values greater than 0.35, and hydrogen bond donor counts greater than or equal to 4. Clicking the search button reveals that there are 32 D3 compounds in the database that meet these criteria. Using these small molecule-based techniques, we've effectively reduced the entire D3 virtual catalog of over 48,000 compounds to roughly 3,000 naphthalene compounds, and then ultimately to 32 naphthalene compounds with chemical properties similar to known REL1 inhibitors. These 32 compounds are excellent candidates for potential synthesis. The third and final general approach I'll discuss involves exploiting knowledge of the protein being targeted. This technique requires a structural model of the enzyme or receptor. Typically, these structures are derived from X-ray crystallography, NMR spectroscopy, or computational homology model building. A number of experimentally determined models are available from the Protein Databank, including a model of REL1 that was determined using X-ray crystallography. Typically, care must be taken in processing these experimentally derived models prior to computational analysis. The details are beyond the scope of this presentation, but generally speaking, models must be refined by adding hydrogen atoms, correcting unlikely geometries, etc. Once receptor models have been prepared, a technique called computer docking can be used to identify potential inhibitors. Docking is a two-step process. First, small molecule models are positioned within the receptor binding pocket. Once a reasonable binding pose has been identified, the free energy of binding is also predicted. The compounds with the best predicted binding energies are then submitted for subsequent experimental testing. To demonstrate, I docked the naphthalene-based D3 compounds with chemical properties similar to known REL1 inhibitors into a carefully prepared REL1 receptor model using a free docking program called AutoDock-Vina. The table on the right shows the 4 best predicted inhibitors with their predicted binding affinities or docking scores. The top-ranked molecule is predicted to participate in a number of important molecular interactions with the REL1 receptor. Specifically, it may form 2 hydrogen bonds with the amino acids isoleucine 59 and histidine 89. Additionally, the negatively charged carboxylate group on the predicted inhibitor may interact with the positively charged amino acids arginine 111 and lysine 98. Finally, the naphthalene moiety of the inhibitor is predicted to form a pi-pi stacking interaction with phenylalanine 209, just as the adenine ring of the endogenous ATP substrate does. Although this docking pose seems reasonable, only experimental testing can confirm the efficacy of this predicted inhibitor. In conclusion, I'd like to acknowledge Martin J. O'Donnell and William L. Scott, who lead the D3 initiative. I'd also like to thank Romy E. Amaro, the principal investigator of the lab where I work. Support from other commercial, governmental, and academic sources is also gratefully acknowledged. Thank you for your time.